To close out this unit, we're going to look at one other type of synthesis problem. And this is what I call a chain elongation problem. We're actually going to look at two problems. So suppose you were given the following problem. Synthesize one butanol from one propanol and any other reagents you need. How would you solve it? Well, like any other synthesis problem, start with the product and work your way backwards until you reach the starting material. So here's our product, one butanol. And since the product is a primary alcohol, we know from our understanding of the reactivity of Grignard reagents that you can make a primary alcohol from a Grignard reagent plus formaldehyde. So the 4 carbons of the product will come from the 3 carbons of propylmagnesium bromide plus 1 carbon of formaldehyde, and the bond in red is the one that's going to be formed in the Grignard reaction. Okay, so propylmagnesium bromide is the Grignard reagent that we need in this case. Now, for this problem, Grignard reagents are not allowed as starting materials. So we're going to actually have to form the Grignard reagent from the corresponding bromide, and you remember that that happens in the presence of magnesium metal in ether. And now the final question we need to answer is there a reagent that can convert 1 propanol, which is the allowed starting material, into 1 bromopropane? And the answer, of course, is yes. There are actually 2 reagents that we have studied that do this. Either HBr or PBr3 will accomplish the desired transformation. So once you've done that level of thinking backwards, then what you need to do is provide your final answer in the forward direction, and it goes like this. Reaction 1 is the reaction of propanol with HBr, in this case to give 1 bromopropane. Reaction 2 is the reaction of 1 bromopropane with magnesium in ether as a solvent to give propylmagnesium bromide. And then finally, in reaction 3, propylmagnesium bromide reacts with formaldehyde. First mix them together in ether, then add aqueous acid to do the workup, and that will give you the final product we want, which is 1 butanol. Okay, I've got one more problem with you. Instead of preparing 1 butanol from 1 propanol, let's prepare 1 pentanol from 1 propanol and any other reagents that you need. This represents a 2-carbon chain extension rather than a 1-carbon chain extension. So you can do this problem using the same strategy as the last problem. You can actually take propanol, convert it to butanol, and then take butanol, convert it to butyl bromide, butyl Grignard, and then add formaldehyde to that again and make pentanol. But as you can tell from what I just said, that will take many steps. And there is a more elegant solution. Organic chemists like to come up with the most elegant route as possible, first of all because it looks nicer when you actually write it out. But second of all, and most importantly, if you want to synthesize a target molecule, you want to do it in as few reactions as possible. Because reactions take time, reactions take effort to purify, and the more reactions you do, the more raw materials you have to put in, and the more chemical waste that you generate. So the need for shorter solutions is not just one of being cute. There is actually a practical need for it. And the elegant solution to this problem is to use an epoxide as a 2-carbon fragment, and therefore we will only have to form 1 carbon-carbon bond. We'll have a 3-carbon fragment and a 2-carbon fragment. Okay, so the retrosynthesis is that the carbon-carbon bond being formed will be the one in red. The 3 carbons in green come from propylmagnesium bromide, which we already talked about how you make from propanol. And then the 2 carbons in blue plus the oxygen are going to come from the epoxide ethylene oxide. So, having done the analysis, the final answer in the forward direction is as follows. First reaction, very familiar, propanol plus HBr giving you propyl bromide. Second reaction, also familiar, propyl bromide plus magnesium in ether giving you propyl magnesium bromide. And then your third reaction is you mix propyl magnesium bromide with ethylene oxide in ether, and then subsequent to that, do the aqueous workup to give you pentanol as the product. Okay, so now we have come to a logical stopping point. We have learned two general strategies for synthesis problems. One is the Grignard oxidized Grignard pattern that allows you to make a tertiary alcohol from simpler starting materials. And now in this lesson, we finished up with the 1-carbon and 2-carbon chain extensions. The idea of synthesis can be applied to much, much, much more complex molecules. There are people who spend 5 years in graduate school getting a PhD working towards the synthesis of one complex molecule. There are chemists in the pharmaceutical industry that spend years and years making molecules looking for active drugs. So the strategy that we've introduced in this unit is one that is central to how organic chemistry is practiced, and there will be more examples of solving synthesis problems as you proceed through the course and put more reactions into your toolbox. And that will allow you to be able to synthesize molecules other than alcohols as being the functional group present in the final target molecule. But in this introduction, you got a flavor of how to think about a synthesis problem and a few examples of patterns to recognize when solving synthesis problems.